Hello friends, I welcome you in lecture number 32 on relations. In lecture number 31, we have discussed about equivalence relation, and we know that a relation R on a set X is called an equivalence relation if that relation is reflexive, symmetric and transitive. And if you have seen lecture number 31, we have seen this type of relation on the set of integers. Suppose R is a subset of Z cross Z, where Z is the set of integers defined as R equal to ordered pair xy such that x minus y is divisible by 3. We have seen that this relation R on the set of integers is an equivalence relation, and that we have shown in lecture number 31. Now suppose instead of 3 we are considering any positive integer which is greater than 1, then we will obtain this relation R equal to ordered pair xy such that x minus y is divisible by small m, where small m is a natural number or positive integer greater than 1. So for every m in this set of natural numbers, we will have this relation R, which is always an equivalence relation. So this is the generalization of that example which we have seen in lecture number 31, and this relation is special relation and it is called congruence relation. CONGRUENCE. Congruence relation is the equivalence relation on the set of integers defined as the collection of all those ordered pairs xy such that x minus y is divisible by m, and we can also prove that this R is an equivalence relation on the set of integers. So this R is special type of relation and it is called congruence relation, and the notation for congruence relation is this type of 3 line segments. So we can write congruence relation as this congruence relation is equal to, let me write properly, congruence relation is nothing but set of all those ordered pairs xy of integers such that x minus y is divisible by small m, where m is a natural number strictly greater than 1, and this relation is called congruence relation modulo m. For different values of m we will have different congruence relations. So we say that R is a congruence relation modulo m or congruence modulo m relation, and whenever xy is an element of R, we write that x is related to y, and here we are using this congruence relation. So this I can represent in this way also, x is equal to y modulo m. So shortly we will write mod m. This we can read as x is congruent to y modulo m, and x is congruent to y modulo m means x order pair xy is a member of this relation, and therefore x minus y is divisible by m. So we will remember that x is congruent to y modulo m if and only if x minus y is divisible by m. In other words, x minus y is divisible by m is equivalent to the statement that m divides x minus y, or we can say that x minus y is integer multiple of m, where k belongs to z. So these are the equivalent statements. X is congruent to y modulo m if and only if x minus y is divisible by m, or m divides x minus y or x minus y is a multiple of m, suppose k into m, where k is an integer. So remember this special relation, it is defined on the set of integers. For different values of m, we will obtain different congruence relations depending on this value of m. So this relation is called congruence modulo m or congruence relation. So that I have written systematically here. They can ask you to write down the definition of congruence relation. So you should write in this way. Suppose m is a positive integer and m is greater than 1. Consider the relation R on the set of integers z defined as R equal to ordered pair xy, where x minus y is divisible by m, or equivalently m divides x. Then this relation R is a congruence relation. R is called congruence relation. This is the notation for congruence relation, and we can write x related to y as x is congruent to y modulo m. We can read this as x equals y modulo m, and this statement x minus y is divisible by m is equivalent to the statement that both x and y have the same remainder when each is divided by m. For example, if you recall the example which we have seen in lecture number 31, we have seen that r equal to x minus ordered pair xy such that x minus y is divisible by 3. So we have seen this type of ordered pairs here. If I take ordered pair 1 4 or ordered pair 6 3, then all these are elements of this relation R. So we can write that ordered pair 6 3 belongs to R, or equivalently 6 is congruent to 3 modulo 3, and this means that if we divide 6 by 3 or 3 by 3, we will obtain the same remainder. Suppose I divide 6 by 3, here I have 6 and 3. So if I divide both the elements or both the components by 3, I will obtain the same remainder. Here we have 3 into 2 6, so remainder is 0. Similarly here also remainder is 0. So this statement that x minus y is divisible by m is equivalent to the statement that both x and y have the same remainder when each is divided by m. And these are different representations which I just discussed. X is congruent to y modulo m if and only if x minus y is divisible by m, if and only if m divides x minus y, if and only if x minus y is integral multiple of m. So I can write x minus y equal to k times m for some integer k. And here this is simple exercise. We can prove that this congruence relation is an equivalence relation on the set of integers. So they can ask you this type of question also. Let m be a positive integer with m greater than 1. Show that the relation R equal to ordered pair AB such that A congruent to B modulo m is an equivalence relation on the set of integers. So we recall that A is congruent to B modulo m. This means A minus B is divisible by m, or m divides A minus B. A minus B is divisible by m, and I want to show that this R is an equivalence relation on the set of integers. That means R is a subset of Z cross Z, and we have to prove that R is reflexive, symmetric and transitive. So we can prove all these three properties one by one. First we write for reflexive property. So for that I consider any integer, say A, in the set of integers. For A belongs to Z, I have to prove that ordered pair AA belongs to R. That is, I have to show that A is congruent to A modulo M, and this is true if and only if A minus A is divisible by M. A minus A is 0, and we can write 0 equal to 0 into M. Therefore 0 is divisible by M, therefore A minus A is divisible by M, and therefore ordered pair A comma A belongs to R for any A in the set of integers. Therefore R is reflexive. So we can write systematically, for A belongs to Z, A minus A equal to 0 into M. This means A minus A is divisible by M. Therefore A is congruent to itself modulo M, and this means ordered pair A comma A belongs to R, and this A is arbitrary integer. Therefore we can write that ordered pair A comma A belongs to R for any integer A, for any A in the set of integers. Therefore we have shown that relation R is reflexive. Second property we have to prove is symmetry. So for that we consider two arbitrary integers. Let AB belongs to Z and be such that A is related to B, or ordered pair AB belongs to R. And to prove symmetry we have to show that whenever ordered pair AB belongs to R, then ordered pair BA is also in R. Now ordered pair AB belongs to R, therefore A is congruent to B modulo M. This means A minus B is divisible by M, and if A minus B is divisible by M, we can write A minus B as a multiple of M, and this multiple is integer k times M, where k is an integer. Now we want to prove that ordered pair BA belongs to R. So B is related to A if B minus A is divisible by M. So here I have A minus B. So to obtain B minus A, I multiply both sides by minus 1. That is negative of A minus B equal to negative of k times M. And this I can rewrite as B minus A equal to minus k times M. And k is an integer, therefore minus k is also an integer. This means B minus A is integral multiple of M, and therefore B minus A is divisible by M, and therefore B is congruent to A modulo M, and therefore ordered pair B comma A is also in R. So we started by considering arbitrary integers AB such that A is related to B, and we have shown that B is also related to A. This means relation R is symmetric. So this is the second property required to prove the equivalence relation. And last property is transitive property. So we consider any three integers. Let A, B, C belongs to Z such that A is related to B, that is AB belongs to R, and B is related to C, that is BC belongs to R. And if relation is transitive, then we must have ordered pair AC belongs to R. So we have to show that if A is related to B and B related to C, then A is related to C. Now AB belongs to R, that means A is congruent to B modulo m, and here I should write b is congruent to c modulo m. A is congruent to b modulo m, that means a minus b is divisible by m, that means a minus b is multiple of m. So I am writing a minus b equal to p into m for some integer p. B is congruent to c, that means b minus c is divisible by m. So b minus c is also a multiple of m, say q times m, and here p and q are integers. Now I want to prove that a minus c is divisible by m. So I have to show that a minus c is also a multiple of m. So now I can write a minus c as a minus b plus b minus c, and here we have a minus b equal to p times m, b minus c is q times m, and therefore we can rewrite a minus c as, we can take m common, and we have p plus q times m, and p and q are integers. Therefore p plus q is also an integer, and therefore we can see that a minus c is an integral multiple of m, and this means a minus c is divisible by m. A minus c is divisible by m, and therefore a is congruent to c modulo m, and therefore ordered pair a comma c belongs to R. So we have shown that whenever a is related to b and b related to c, then a is also related to c. This means R is transitive. Therefore R is reflexive, symmetric and transitive. Therefore R is an equivalence relation. We have shown that congruence relation is an equivalence relation. So they can ask you to prove that congruence relation is equivalence relation on the set of integers. So you should remember this definition of congruence relation. They may not write this definition. They can directly ask you that prove that congruence relation is an equivalence relation. Then you should remember the condition of congruence relation, that a is congruent to b modulo m if and only if a minus b is divisible by m. Instead of m, they can give you any particular value of m, and if they are asking for particular value of m, you should write for that particular value of m, as we have seen for m equal to 3 in previous lecture. So remember this congruence relation, we are going to use this relation in upcoming lecture also. And this is all about this session. I hope you like it. Thanks for watching.